Okay, let's wrap up this unit on angular motion. So we have a playground merry-go-round, which is basically a spinning platform. Has a mass of 200 kilograms, a radius of 1.5 meters. It's rotating in the counterclockwise direction, which remember is the positive direction, the right hand rule. Curl your right hand, your fingers of your right hand in the direction of motion, and your thumb points in the positive direction. Okay, at 4 radians per second. What is the moment of inertia? Well, because in order to use any of these equations, we need to know the moment of inertia of the object in question. So, moment of inertia of a solid disk is 1/2 mr squared. So I have 1/2 the mass of 200 times the square of the radius, which gives me a moment of inertia of 225 kilogram meters squared. And I'm just going to use this exact same platform throughout this exercise just to simplify things a little bit and focus in on the concepts. So what is the angular momentum of the merry-go-round? Well, the angular momentum, which is L for whatever reason. Hang on a second, I got to get my phone. Alright, so where were we? Oh yes, angular momentum, which is L times the moment of inertia times the angular velocity. So we're going to use L equals I omega, and I'm looking for L, so I, we figured out, and we're going to use this throughout this homework, is 225. It has an angular velocity of 4 radians per second. So just like mass times velocity equals momentum, I times omega equals angular momentum, 900. And the units are kind of unwieldy, kilogram meter square per second. Ugh. So, number 2. Now this one's kind of weird, all right? So a baseball is going in a straight path, and it passes over the merry-go-round at 34 meters per second, making a 20-degree angle to the radius of it. So I want to know, what is the angular momentum of a baseball? And I get it if you're feeling like, well, how can an object that is traveling a straight line have an angular momentum? But, you know, if you pick a point in space and look at the path of this baseball, it is traveling at an angle to that, so it does have angular momentum. It may not be going around in a circle, but it's still traveling through an arc. So what we do then is we say, in this case, we're going to use this relationship here, where we say the moment of inertia in this case is equal to the mass of the object times its position relative to that point in space. So how the radius between it and the point we're arbitrarily choosing to measure its position from, the velocity of the object, and the sine of the angle it makes to the line of action. So we have a 2 kilogram baseball. It is passing over the merry-go-round, which has a radius of 1.5 meters at 34 meters per second, and it's making an angle of 20 degrees to the radius of the playground equipment. And so I just multiply these out, and I get an angular momentum of 34.9 kilogram meters squared per second with respect to the merry-go-round. Now, that's a useful thing in solving all of these problems, as we'll see. Fortunately, the angle is not going to be 20, it's going to be 90 in most of the problems you get. But in this case, I made it 20, just so you see that you actually have to use sine of theta sometimes. So, now I have a person standing on the outside of the merry-go-round, which is initially at rest. The person is going to jump off. And so what's going to happen is, as the person jumps in one direction, the merry-go-round is going to spin in the other direction. They both have angular momentum. And remember, this is a quantity that is conserved. The conservation of angular momentum is one of the most important concepts in physics. However much angular momentum you have to start with is what you're going to end up with. So let's start this. What is the person's angular momentum with respect to the center of the merry-go-round? So the person has 55 grams of mass. They are moving at a velocity of 4 meters per second. They are 1.5 meters away from the center of it, and they're jumping at a tangent to the circle, we are to assume, well, we're told actually. So therefore it's sine of 90, which is 1. And so that gives me, or this person rather, an angular momentum of 330 kilogram meters squared per second. Therefore, since the, and that's, by the way, since it's going this way, that's the equivalent to a clockwise rotation. That would be, really, it should be a negative value there. Therefore, the playground equipment has to have a positive 330 kilogram meters squared second angular momentum. So let's just go to this next part and see what happens here. Okay, so what we're going to do is we're going to use this relationship here. I'm going to say, well, this is the momentum of the playground equipment, the angular momentum. Here's its moment of inertia, so we're just going to solve for its angular velocity. And when we do, we see that it ends up spinning in the counterclockwise direction at 1.47 radians per second. I think it's pretty cool, actually. Alright, now look at this next one I thought up. I love this one. So I got a rocket that's bolted to, a massless rocket, by the way, from our massless frictionless door. It's bolted to the rotating platform, and it's 0.8 meters away from the center of it. And because its thrust is at a 90-degree angle to it, it's going to cause this to want to spin this way, which is in the negative direction. So what we have then is this massless rocket is 0.8 meters away from the center, and it's applying 45 newtons of force this way, creating a torque. And so what we want to find out is, let's see, if the rocket fires for 60 seconds and the platform is initially at rest, what will the final angular velocity of the platform be? So first we need to figure out what is the torque that this is placing on the system. So the torque, if you recall, is equal to force times radius times sine theta. So the force is 45 times the radius times sine of 90 gives us 36 Newton meters of torque. Now what I'm going to do then is I'm going to use the angular equivalent of the impulse equation. So if you recall with impulse, we would say force times time equals delta mv. Now we're going to say torque times time equals delta I omega. So the torque was 36. The amount of time in seconds that torque was applied was 60 seconds. So this is the impulse that's going to change the angular momentum here. The value for the moment of inertia is going to stay constant throughout this homework, 225, and therefore I'm just looking for the change in its angular velocity. So when I solve this, what I'll get is, well, I should have made this negative 36, shouldn't I? Because what I get is negative 9.6 radians per second, because clockwise equals negative. So I sort of screwed up. I should have made that a negative 36. Alright, so then let's look at the next thing here. What would the final angular velocity of the platform have been if it had initially been spinning counterclockwise in the positive direction at 5? Well, remember, what we're solving for here is a change. You see that delta there? We're looking for a change in the angular velocity. So the angular velocity changes by 9.6, by negative 9.6. So I had 5. Combine that with negative 9.6 gives you negative 4.6 radians per second. In other words, it was going this way. The rocket fired, slowed it down, and made it start going the other way. And it ended up going 4.6 in the clockwise direction as opposed to its original direction. Now let's see what I have here. I have a 75 kilogram person standing on a merry-go-round. You might have done this. The person is standing 1.2 meters away from the center of the platform, and they walk towards the center and end up at 0.5 meters away from it. So as they move inwards, it's going to obviously spin faster. If you've ever been on a rotating platform, you've experienced that. So what we had to do now is we had to use the conservation of angular momentum. And this is a big idea in AP Physics. This is a huge one that they are definitely going to make sure you are solid with. So the sum of the initial angular momentums equals the sum of the final angular momentums. So what is our initial angular momentum? Well, initially we have two things. We have a person who's spinning, and we have a platform that's spinning. So let's start with the person. The person has 75 kilograms of mass. I'm going to have to use this equation here since the person is rotating and has an angular velocity. If the person's not rotating, you use this to find their angular momentum, but when the person is rotating, I'll use this one. So I basically just, notice that's a pretty familiar looking thing there. mr squared is the person's moment of inertia. So I say 75, the person's mass, times 1.2, the radius squared, times 3, which is the angular velocity of the person. So that's the momentum, the angular momentum of the person. Now I'm going to find the angular momentum of the platform. Its moment of inertia is 225, and its angular velocity is 3. So basically that's going to give me 324 plus 675 is the initial. Now, The final one is going to be the person's mass times the person's new position, which is now 0.5, and I have to square that because it's radius squared. So essentially what's happened is the I of the person has changed. This is the momentum, the angular momentum of the person. This is the angular momentum of the platform. And so I can just take the omega out of here and say omega equals 75 times 0.5 squared is 18.75 plus 225. And when I then take this and solve it for omega, I get 4.1 radians per second. And look, it makes sense because it was going 3, the person moved towards the center, and the thing spun faster. Now, look at number 6. This might be a little bit more familiar to you. If you've ever watched the Winter Olympics, you've seen ice skaters who are spinning slowly, bring their hands and legs in, and they spin faster. So if an ice skater starts out with an angular velocity of 8 radians per second, brings her arm inward and reduces her moment of inertia to half of what it originally was, basically what happens is if I goes down, omega goes up. If mass goes down, velocity goes up, essentially. And since her I went down by a factor of 2, her angular velocity goes up by a factor of 2. So it increases to 16. And that's basically what's happening here, that the I is getting smaller, so the omega is getting bigger. Our next one here, all right, let's see what we've got here. Platform is spinning at 7. We're going to drop a boulder onto the center of it. Okay, so the first thing I've got to do is figure out what is the I of the boulder. What is the moment of inertia of the boulder? That's going to be, it's a solid sphere, so it's 2/5 mr squared. 2/5, 650 is its mass. R squared is 0.39 squared. That gives me 39.5 as the moment of inertia of the boulder. So, the sum of the initial angular momenta equals the sum of the final angular momenta. So initially what we had was our spinning platform, which has a moment of inertia of 225, and it's rotating with an omega of 7 radians per second. I drop the boulder on it now. So now the two momenta afterwards, the momenta of the boulder, which is I times omega, is going to equal plus the momenta of the platform, which is I omega. And I'm going to pull omega out of here, so what I get is 1575, which is what I get when I multiply this, equals 264.5, which is what I get when I add 39.5 and 225, times omega. And when I solve for omega, I see that the platform is now spinning at 5.95 radians per second. Hey, that makes sense. It was going 7. I put a massive object in its center, and now it's spinning a little bit slower. Alright. Now, the rotating platform is at rest when a 65 kilogram person runs at 6 meters per second and jumps onto it. He lands at this radius, at this angle to the radius. So, this is basically a very common kind of problem to ask you. So, again, I'm going to use conservation. Sorry about that. I'm going to use conservation of angular momentum. So, let's see. Since the platform is at rest, it has an initial angular momentum of 0, so I'll just ignore that. So let's find the angular momentum of the person. The person's not rotating, so I'm going to have to use this relationship here. This relationship here to figure out what is the person's angular momentum. So the person's angular momentum is going to be a mass of 65 times a radius of 1.3 times a velocity of 6 times the angle of 80. Take the sine of that angle, and what you get is the person's initial angular momentum is 499.3. That's the total angular momentum of the system beforehand is going to equal the total afterwards. So afterwards I have two objects now. I have the I omega of the platform, and I have the I omega of the person. Now the person is rotating in this case, so now the person is rotating, I'll have to use this relationship for the person's angular momentum. Mass R squared omega, since the person is rotating. And that's a little bit tricky, but you can handle that, right? So I'm going to multiply 65 times 1.3 squared, and I get the moment of inertia of the person is 109.9 plus the moment of inertia of the platform times its angular velocity is going to equal this momentum. Solve that for omega, and you get 1.49 radians per second. So the platform wasn't spinning, the person jumped on it, and now together they are rotating at 1.49 radians per second. And this last one is, again, quite the classic. What I've got is a ball that is going to move this way and then bounce off of here. And this is going to rotate when it gets hit. It's going to start rotating this way. So what I have here is an object that is not rotating, so I have to use, and that's the only angular momentum to start with. The total angular momentum to start with is that of the ball. So I'm going to take the mass of the ball times the radius of the ball, which is 1.4, where it strikes, times the velocity of the ball, which is 5 meters per second. And since this is going to cause a rotation this way, I'm going to call that a positive velocity, times the sine of 90, since it's striking at a right angle. That's the total momentum of the system to start with. The angular momentum to start with is 5.6. Now, I have two objects afterwards. The ball is moving this way afterwards, which is the equivalent of a negative rotation. So I'm going to say 0.8, which is its mass, times 1.4, which is its radius, times negative 1. Its velocity is now in the negative direction, times the sine of 90. And now I was told that the moment of inertia of this rotating part of the system is 2.61, so 2.61 times omega, and so I just have 5.6 equals negative 1.12, which is what this all turns into, plus 2.61 omega. So I have to add this to both sides. So when I add 5.6 and 1.12 and then divide it by 2.61, I find that this object here is rotating this way at 2.57 radians per second.